So alright, in the previous page I have shown you how to do this dynamic programming based query optimization already, right? And in these coming pages we will show you the more detailed information how to explain how to implement this kind of algorithm based on some concrete functions as well as some concrete operations. And here in this section, we are starting the same problem we mentioned before. Given the relations, we want to calculate the joins among them. And we want to find the base query logical plans as well as the join trees for the queries, right? And we want to implement this algorithm implementations with this dynamic programming algorithm instead. According to the previous page, we do the dynamic programming in the bottom-up manner, right? So based on the individual relations, we want to combine them together and to find the base logical plans for the subset of the relations. We also mentioned to implement this algorithm, we need to implement a function. It is a cost function, right? Which will be used for evaluating the combination of the subset of the relations, which will be the base or beta, right? We will evaluate this then based on this cost function. Alright, so in this page, we will show you with some concrete mechanisms we can use for implementing this algorithm. Given the relations, so R1 to Rn, right? For each subquery Q, which we also join query, and this join query will cover a subset of relations from this R1 to Rn set. And we want to compute the following. So the first term we want to calculate is the size of Q, right? So given the relations covered by the Q, we want to calculate the size for implementing the Q, right? The subquery. And we also want to find a beta plan for this subquery Q, which will be denoted by the plan Q, right? And at the same time, we also have to define a cost function for this Q, which can be denoted by cost Q, right? It measures the cost for implementing this subquery. So, this Q can be a subset. It covers both the individuals as well as overall its relations, right? So, according to the previous page, we want to implement this program. We want to implement this algorithm from the bottom up, right? Therefore, for step 1, we have to calculate all these three terms for individual relations covered in this set, right? Therefore, in step 1, we want to calculate for each relation Ri. We want to calculate the size of Ri will be equals to what? Equals to BRI, right? I hope you still remember this notation, BRI. It denotes the number of blocks it belongs to this relation, this Ri, right? At the same time, we also have to design a plan, this join tree or the logical plan for this relation, for this subquery, right? So, because right now we only have one individual relation, and if we plan to calculate the joins for it, it will actually be equals to Ri itself, right? Because we only have one single relation, we cannot compute the joins. Therefore, the plan for this Ri individuals will be equal to Ri directly, and the final term will be the cost, right? So the cost for the subrelation or subquery will be on the Ri will be equal to the cost for scanning this Ri, right? We already mentioned this before, because when we are loading the relation into memory, we have to scan it, right? The cost interest in joining one single relation will be equal to the scanning cost for this relation. So this will be the three terms we defined before for the individual relations when we are doing a subquery covering one single relation, right? It is for step 1. And besides step 1, we can further, go upward because we are doing it from the bottom up manner. We can further calculate the more combined relations. We want to compute their cost as well, which will be shown in the next page.